Let's look at the conditions that go behind the different patterns that we see for a binomial situation. There's three really important things that we need to look for. One is that the probability of success cannot change at any time. What that means is, for example, if you're flipping a coin, the probability of getting heads is 0.5 on the first flip, 0.5 on the second flip, 0.5 on the third flip. It never changes. From flip to flip, the probability stays the same. If you're using this for humans situations like a basketball game, you're making kind of a shaky assumption that people's free throw percentages stay constant, that they're not affected by if I miss a shot, now I lose confidence, things like that. So with binomial distributions dealing with humans, sometimes you have to be a little bit careful on what you're assuming. Second one is results must be success or failure and nothing in between. You either make the basket or you miss it. You either get a heads or you get a tails. Which one you choose to be success and which one you choose to be failure doesn't actually matter. So if you decide that tails is success and heads is failure, that's okay. The most important thing is that there are exactly two outcomes, and one of them is the one that you're looking for. The last thing is that the number of attempts that you're going to count have to be determined before you start counting. For example, I'm going to flip the coin 4 times, and it doesn't matter how many heads or how few heads I get. You're not allowed to say things like, I'm going to flip a coin until I get a heads, or I'm going to shoot baskets until I miss. That would not follow a binomial distribution. In order to be binomial, you need to decide ahead of time how many shots you're going to take, how many coins you're going to flip, how many rows are going to be in the Plinko game. Now, if you want to apply this to the coin flip, in the first situation, we would say that you have a 50% chance of getting heads on any flip. So on a single flip, P, the probability of success, is 0.5. And we're going to use P as our probability. Next one, the success or failure. I've decided that heads is going to be success, tails is going to be failure. It doesn't matter, like I said, you just have to be consistent when you do it, but that's what I decided to make it. And then the last one, number of attempts, has to be determined ahead of time. Let's say you're going to flip 8 times. So you're going to take 8 coin flips and you're going to count up how many heads you get. Now let's take these same rules that we just talked about and let's see if we can apply them to sampling distributions, because it turns out that the same idea happens when we have proportions. The probability for success is not allowed to change. When you're talking about that, that would be analogous to saying the population, whatever population you're studying, has some set proportion that you're trying to find. So let's say you're doing a study of the high school and the proportion of students who like ice cream is 96%. You don't know that ahead of time, but it's something that's set and you're trying to figure out what it is. So that's why you take samples, is to try to predict what that population value really is. The success or failure with nothing in between, we're asking some sort of yes/no question. Do you like ice cream or do you not? There's only 2 options, so we do have success or failure. And in this case, I might say success is someone who likes ice cream. That's what I'm looking for, is how many people do like ice cream. And then the last thing is the number of attempts to count has to be ahead of time determined. And in that case, that would be your sample size. So I'm going to sample 10 people from the population. And so the binomial distribution turns out to be a good basis for how both StatKey and different calculators can predict, and different formulas can predict how likely you are to be correct, how you can calculate, let's say, a p-value in a hypothesis test, or the size of an interval when you're doing confidence intervals. This is all underlying based on the binomial distribution. Defining n and p is always going to be an important thing to start with whenever you're doing a binomial problem. So n, we said, is the number of trials you're going to do. P is the probability of success. We're going to do an example situation here where we are going to be shooting free throws. So we've got our free throws. That's our beautiful basketball here. Shooting from the free throw line, standing so many feet away, and we're going to try to see how many we can make. The number of shots we're going to take is predetermined, and that's going to be 5. So we're going to take exactly 5 shots from the free throw line with our oversized, ugly basketball. And then our probability of success, let's say you're a 70% free throw shooter overall. So we're going to use that as our starting point. Now, binomial probabilities are best calculated with a calculator, ideally a TI-83. There are other ways to do it by hand, but it's just a lot of work, so it's generally not worth it. So the probability of a single value can be calculated using the function in your calculator called binompdf. And so if I go back to my home screen here on my calculator, and I go to second vars, and what second vars is, that's the distributions up here, and you'll see normal CDF, but if you go down a little ways, you're going to see binompdf and binomcdf. And so binompdf is A, binomcdf is B. It might be a little bit different depending on the version of your calculator. But the binompdf is what I want first. So I'm going to hit that. And then it asks for n followed by p followed by x. We said a second ago that our n is 5 and our p is 0.7. So we're going to type in 5, comma, 0.7. But then it also wants x. And we know that this is our number of trials. This is our probability of success per trial. X is how many successes we're looking for. So the probability of making 0 out of 5 free throws is going to be when x is equal to 0. So if I type in this, we're going to get the probability of making 0 free throws. 0.00243. And what that tells us is that it's incredibly unlikely to make 0 out of 5 if you are a 70% shooter. Now, save myself some time since I'm going to do this for 1 through 5. I can hit second enter, and it will type in exactly what I had before. And I'll just change that 0 to a 1. And now I have 0.02835, I believe. And you can keep on going, and I'm going to just do these real quick, but you can do these each on your own. And once we've got these all figured out and filled in, you can see that the most likely one is 4 out of 5, followed closely by 3 out of 5. And if you're a 70% free throw shooter, that would make sense that you're probably going to make either 3 or 4 out of 5. Now, on the high end, you get kind of bunched up along the edge here, so there's about a 17% chance that that's going to happen, that you're going to make them all. And it's always possible that you'll miss them all, just incredibly unlikely. Now, it's a lot easier to look at this data graphically than it is in a table. So if you were to make a simple chart of this, you've got 0.02, which is going to pretty much not even show up here by 0. 0.028, also very small, just kind of a little blip down here. 0.132, we're very low probability for that, right in there. 0.309, so now we're all of a sudden getting up into the more substantial probabilities. And then 360, again a little higher, and then 168. So all I'm doing is making a simple bar graph out of this data here. And the reason I'm making a bar graph instead of, let's say, a histogram is because it is discrete data. Each value does take on a different category. It's not me deciding where I'm going to put my bins like I would with a histogram. It's all put together. So finish that up here, and then we can go back to our probability chart, and there's one more function that we're going to use a lot, and this is the binomcdf. So different than the PDF, we are doing CDF here. And the difference with C, the C stands for cumulative, which means that we accumulate everything at or below that number. So for the 0, we're going to figure out the probability of being at or below 0 successes. And so that we go to that second vars, that second dister, and we go down a ways to binomcdf this time. And what we'll do is we'll type in the exact same sequence that we did before with the PDF. N, P, X. So slide that over here. We're going to type in n equals 5, p equals 0.7, and then x is 0. And you'll see that we get the same exact result, the 0.002 that we got before. Now if you're wondering why are we doing this if we're getting the same result, you'll notice that that's going to start to change as we go up. So we hit our second enter, we do 1, and you'll see we get 0.3 or 031. 0.031. And let's do one more just to kind of show the effect here. If we do it for x equals 2, then what we're going to see is 0.163. And these numbers are growing faster than the numbers on the left. It's actually accumulating everything at or below its given value. So, for example, this 0.31 is actually these two added together. And this 0.163 is all three of these added together. These equal 0.03, and then be 0.162 roughly, and with a little rounding error, 0.163. So you can see how the CDF takes not just this x is 2, but also x is 1 and x is 0. It takes everything at or below a given value. If you look at the graph of the cumulative function, what you're going to see is that unlike the original distribution where it curves back down, knowing that the expected probability is probably somewhere around here, the cumulative is just going to keep going up. And that's true of any cumulative function that you'll see in probability. It keeps accumulating everything at or below it, such that when you get to the last one, it should be at 1.0. It should be at the highest. There's a 100% chance that you're going to make 5 or fewer free throws, which obviously makes sense. There is a 83% chance that you're going to make 4 or fewer, and it goes down from there. So the idea of the cumulative function is that it just accumulates everything at or below it.